Hi everyone and welcome back to the AutoLightSleep. In earlier videos I have been talking about the ESP32-C6 and its Wi-Fi 6 power saving features that are supposed to benefit battery powered Wi-Fi devices. For this video I made a little application that uses the ESP32-C6 dev kit and a few sensors which I'm using to explore how much power we consume using Wi-Fi 6 power saving modes compared to the more traditional Wi-Fi saving power modes. To be more specific, in this video we are comparing the Wi-Fi 6 high efficiency mode using individual target wake time with AutoLightSleep versus deep sleep. For those of you that are interested in details on what version and settings I have used and how to tweak the software, I have added a section at the end of this video. So let's get into it.
A quick sponsorship statement. All tools and equipment you see in today's video have been purchased by me with my own money and are not in any way sponsored by anyone. I'm also not getting paid or getting products or services in exchange for my opinions and thoughts in this video.
Let's take a closer look at the application. Let's assume we are simulating a battery-operated device. In between the reporting intervals, the device is sleeping to conserve battery power. We are using Wi-Fi to report temperature, humidity, and light information. We are using MQTT to provide the data to the user. The data flow will look like this. Our ESP32-C6 will get the data from the temperature humidity sensor and the light sensor. We'll publish it over MQTT to an MQTT broker, which I subscribe to with my MQTT Explorer to visualize the data. Quite simple setup. To complete the software design part, let me walk you through the state machine I have chosen for this example. Everything starts with the boot of the system. The bootloader loads the application. Once the boot process is done, we initialize the system. That's drivers like I2C, non-volatile storage, and so on. After the init, we try to connect to our Wi-Fi access point. Once we have a Wi-Fi connection to our access point, we try to connect to the MQTT broker, or as I refer to it here, the backend. When that connection is established, we turn on the 3.3 volt for the sensors and read the sensor data. Then we try to publish it via MQTT to the broker. After all data has been published, we are entering the sleep state. Depending on what method is configured, we either go into deep sleep or AutoLightSleep. The wake up after the sleep differs quite a bit between deep sleep and AutoLightSleep. The deep sleep is almost a full boot, so after a deep sleep we need to go through the boot, init and Wi-Fi connection status. With AutoLightSleep and individual target wake time on the other hand, we wake up and we are right back in the Wi-Fi connected state, assuming we didn't lose the Wi-Fi connection during sleep. But that is the whole point of individual target wake time, that we do not lose our connection. To complete the picture, last is the error state. Whenever we run into an error, depending on the mode, we either stop and print the error message for debugging, or we are rebooting. Okay, with that clarified, let's look at the hardware and measurement setup. I'm using the Power Profiler kit from Nordic to power the entire system. The Power Profiler kit outputs 3.3 volts and at the same time measures the current consumption of the system. I have connected the 3.3 volts to the red pin on the ESP32-C6 dev kit. By using that pin, we are only powering the room module. The rest of the board, like the LDO and the UART bridge, they are actually not powered through this 3.3 volt. So when measuring the current consumption, we are only measuring the current consumption of the C6 room module. The ESP32-C6 can turn on and off the 3.3 volts to the sensors. That is quite important for the sleep mode, so when we are sleeping, we don't want to have the sensors powered. I'm using the SHT40 temperature and humidity sensor as well as the TSL2591 light sensor. Both are connected via I2C. everything looks nice and tidy on the picture. In reality, my breadboard doesn't look that nice, but it's working. So here we have the ESP32-C6, the power profiler kit, the temperature and humidity sensor from AutoLightSleep. No, actually that's the light sensor from AutoLightSleep, and the temperature sensor and humidity sensor is from AliExpress. And then down here we have the power switch that I have put together to turn on and off the 3.3 volts to the sensors. So let's look at some measurements. I'm starting to measure the deep sleep power consumption. The reporting interval is set to 30 seconds. As you can see, we're consuming 8.6 microamp. According to the data sheet, in deep sleep, the room module should consume something around 7 microamp. So we're not quite there, but close. So now I'm recording for 30 seconds. That will give us the average power consumption for one report every 30 seconds. Just a note, for the measurement series I have been measuring several intervals and have taken the average. I'm just showing one here, otherwise it would take too long. So here we can see that after around 30 seconds we have an average of 4.72 milliamps. So let's take a look at the data coming in on the MQTT broker. On the left hand side is Visual Studio Code with a terminal open, and right now we are sleeping, and on the right hand side is the MQTT Explorer showing the data already received. So now the device woke up from deep sleep and reported data via MQTT again and went to sleep again. So there you can see we have the ambient temperature, we have the humidity, and we have the light, and yeah, it's coming in every 30 seconds. So this is in my office at my desk. Okay, let's have a closer look at the deep sleep report in the power profiler again. Zooming in on our wake up period here. So waking up, connecting to Wi-Fi, sending the data via MQTT and going back to sleep again took around 2.12 seconds. That will be interesting to compare to the other sleep method. Alright, now that we know how much power we consume for a 30-second interval, let's put that together with the data for the other intervals into a graph. Here is the graph for the deep sleep power consumption. As you can see on the x-axis, there's the deep sleep intervals in seconds. So at 30 seconds we have a power consumption of 4.72 milliamps or 4720 microamps. So as you can see, as the reporting interval gets longer and the sleeping time gets longer, our power consumption goes down. So at 900 seconds or 15 minutes, we are consuming in average 188 microampere for one report. So now let's do the same with individual target wake time and AutoLightSleep. So let's go back to the power profiler and take a measurement with individual target wake time and AutoLightSleep enabled. The reporting interval is again set to 30 seconds. We should see a power consumption of around 35 microamps in AutoLightSleep, but I did not manage to get it that low in the application yet. We can see some weird wake-ups here which are not the actual data reporting, but I will explain that in the deep dive section at the end of the video. So here we are close to 30 seconds and now we have seen the reporting, which is much shorter than in deep sleep. And now after around 30 seconds we are at 1.48 milliamps in average. So zooming in on the reporting we have seen, I'm measuring 907 milliseconds for the entire reporting. If we now add these measurements to the graph, we can see that the power consumption using individual target wake time and AutoLightSleep is significantly lower than using deep sleep. What you can see here is that my measurements actually stopped after 300 seconds or 5 minutes. The reason for that is that I found an issue with the router I'm using. I believe it's a bug, but more details on that in the deep dive section. One question is, when would the deep sleep be more power efficient than the individual target wake time? In order to do that, I extended the lines by calculating the next values. The picture looks like this. Now I have extended the individual target wake time line with calculated values beyond the 5-minute reporting interval. It's a darker green line. So we can see that in theory, individual target wake time would still be below the deep sleep power consumption even after 15 minutes or with a 15 minutes reporting interval. So how does it look when we are going to reporting intervals beyond 15 minutes? Here on the x-axis we have the reporting interval in minutes now, from 15 minutes to 90 minutes. And we can see that both are actually even in power consumption, around 60 minutes. After that, the deep sleep has a lower power consumption than the individual target wake time, in theory. That also makes sense. Over time, the longer the interval gets, the lower sleeping current has to have an effect on the overall power consumption. Even though these values are only theoretical values, we have seen in the first graph that individual target wake time consumes significantly less power up to a certain point. Why is that? Let's have a closer look at the individual reporting measurements I have taken. On the left hand side we have the close-up of the deep sleep wake up and reporting. So as you can see, this one takes 2.12 seconds, and almost a third in the beginning of the graph is about waking up. Then we are reporting on Wi-Fi. So getting a Wi-Fi connection and reporting takes 2.1 seconds. If we compare that to the AutoLightSleep and individual target wake time, we wake up, we establish the connection to the backend immediately, read out the sensors and report and go back to sleep. Again, this could be optimized in both cases, but it shows the idea behind individual target wake time, so that you don't need to boot again and you don't need to establish a Wi-Fi connection again. Working with the ESP32-C6 and individual target wake time for a while, my conclusion is as follows. It's a promising technology with imperfections. Using individual target wake time, the power consumption is reduced up to 68% in my example. So I think this shows how powerful this technology can be for Wi-Fi battery operated devices. Imperfections because it does not work perfectly out of the box. My router implementation has limitations, or even a bug as I see it, and the ESP software needs tweaking to reach the power consumption that I have shown in my examples. So I hope you enjoyed that video, and for those that are interested in all the details on how to tweak the software, what the bug on my router is, etc., let's get into the deep dive section. Let's start by looking at the ESP-IDF settings I am using. I'm using ESP-IDF version 5.2.1. The menu config settings that impact power consumption are power management needs to be enabled, obviously, the power down of the MAC and the baseband, the Wi-Fi power save type has to be set, dynamic frequency scaling has to be enabled, and FreeRTOS ticklers has to be enabled. Let's look at them in more detail. So let's go through them one by one. Here I have Visual Studio Code open with my application, my Wi-Fi Sense code. Opening the SDK, we start with the power management enabled. So we need to tick support for power management. That one of course has to be enabled. I have power down CPU and light sleep as well enabled. And if we look at the next one, the Mac, we need to enable power down of MAC and baseband of Wi-Fi and BLE when the physical part is disabled. The next one is about the Wi-Fi power save type. So if we look at my Wi-Fi init function here, I'm setting the power saving mode here, and there's different modes you can set which impact the power consumption. So if we look at the different types, none, minimum, and max power saving. All of them have an impact, obviously, on the performance. As you can see here, as it states, the listening interval will be impacted if you change the mode. Okay, the next one is about the dynamic frequency scaling. So if we look at the settings, this has to be enabled. Enable dynamic frequency scaling. So what does it mean? That means that it's possible to scale or change the CPU frequency. That comes with a cost. It increases the interrupt latencies. And one important thing is that the APB, or the Advanced Peripheral Bus Frequency, can change multiple times, which can impact some peripherals. For example, the I2C will be impacted. There are different ways of handling this. In my code, I simply disable power management, do the I2C stuff, and then enable it again. Okay, the last one is about the FreeRTOS. So if we look at FreeRTOS, there is the tickless, where is it? One sec. Which has to be enabled. This one. That means that FreeRTOS will not generate the periodic ticks interrupts. So in order to go into AutoLightSleep, that means all other tasks that could run should be paused or sleeping, and no other interrupts should occur. Then AutoLightSleep can be entered. Okay, now we have set everything for lowest power consumption. But out of the box, these default settings, or even changed settings, will not give you the lowest power consumption for AutoLightSleep. And why is that? That is because we have a DHCP timer and an ARP timer that are running quite often. And in my opinion, they're not needed if we are using individual target wake time. At least they're not needed to run that often. Another point is that individual target wake time has as such nothing to do with AutoLightSleep. So they are not synced, meaning we can easily go into an AutoLightSleep without using individual target wake time, and vice versa. So these are two different concepts that you and your code have to match timing-wise. I hope in the future that Espressif would give us some handle when the individual target wake time has expired, to also start the application code. Let me show you how it looks with the default settings for the DHCP and ARP timer. Okay, so let me show you how the power consumption looked like with the DHCP and ARP timer default settings. So as you can see, we have a bunch of wake-ups here that consume power. So some spikes every second and something in between. So obviously this will impact our power consumption quite a bit. So if you look at it, if I zoom in on one of those, you can see it's not much, but we wake up, do something, and go back to sleep. So now let me show you how to change those. Okay, we are back in Visual Studio Code. Here in the SDK configurator. If you search for ARP you're getting the up timer interval. Here it's set to 10 seconds, but you can change that to, I think, also 60 seconds or more. The other one is the DHCP timer, which can be set from 1 to 10 seconds. But I don't see why only 10 seconds, because if we are sleeping, let's say, for 5 minutes, and we don't have a Wi-Fi connection anyway, so why would we wake up to renew our IP address? If you want to change that one, then you have to go into the kconfig file of the lightweight IP stack. So you can find that where you have the ESP IDF framework under components in the folder of lightweight IP, and then there's a kconfig file. So if you search for DHCP, you need to look for this one. So you can change the range to, I don't know, 120, whatever limit you want to set. So you can see the default is 1 second. If you want to know where you could also change the ARP timer, it is in this file, in the etharp.h. You can find that under components, lightweight IP source include lightweight IP, and then etharp.h, where you can also change that one. The last part of the deep dive section is about my access point or router. I am using the Asus AX3000, and the target wake time intervals beyond 5 minutes are a problem. I'm using Wireshark and sniffing on my Wi-Fi communication, and that reveals the issue. Let me show you. So let's look at the PCAP file, my Wi-Fi sniffing I have done. So here we have some communication between the ESP32-C6 and the access point. So some authentication, that is after the wake up. So we get on the Wi-Fi, we exchange the keys and all that stuff. Then the ESP32-C6 starts to talk to the Raspberry Pi, which is running the MQTT broker, so all fine. And then we're going down to a point where we establish the target wake time session. So that is here. We get a request, or we send the request from the ESP32 to the access point to request a target wake time session. And we are requesting somewhat 6 minutes. So the formula for that is mantissa times 2 to the power of the exponent. And that's done in microseconds. So 5.99 minutes we are requesting here. And as a reply from the access point, we get an accept with these settings. So just a side note, even though we are requesting these settings here in our request towards the access point, that doesn't mean that the access point replies with those. That is a suggestion from the device, but not necessarily accepted by the access point. So always take that into account and check what you're getting back from the access point. Okay, so a little bit of communication going on until the device goes to sleep here. So here we have the timestamp, 22 seconds, we go to sleep. And then we can see that after 320 seconds, 5 minutes, 20 seconds, the access point starts to de-authenticate us, even though we agreed on 6 minutes. And then we are, of course, waking up. After our sleep time, we try to establish a connection, assuming, yeah, we still have a Wi-Fi connection, but we don't. So we need to go through the authentication, the normal procedure again. So clearly, why does the access point accept 6 minutes and then starts to de-authenticate us after 5 minutes to 20 seconds? So that's, in my opinion, a bug. So then I tried to figure out how what's the max sleep time of the access point, and everything above 8 minutes something results in a rejection. Not that it's really important, because we get deauthenticated after 5 minutes 20 seconds anyway, but there's a little workaround to this. But just to show you how it looks if you are requesting, if you're requesting beyond what the access point supports, then it looks like this. So we have a request of exponent is 14, and this is our metizer, so that should be something above 8 minutes, 9 minutes. And then the reply from the access point is here, which says reject, which is fine. Okay, it doesn't support it, but it should at least support 8 minutes. But yeah, it deauthenticates us after 5 minutes, 20 seconds. Okay, so last part, let me show you how you can get around this deauthentication in the code. Quite simple. Okay, so here we have the code that I'm using as a workaround. That's this part. So the main task is sleeping, and basically after 5 minutes, if we have a sleep time above 5 minutes, we wake up and we are sending a probe, just a small probe, and then we're going back to sleep. This small probe, of course, has a power consumption, but it's very small, and we only have to do it every 5 minutes, and that actually keeps the connection with the access point, so it doesn't deauthenticate us after 5 minutes 20 seconds. I tested that works quite well as a workaround. Not ideal, but it works. So I hope this was helpful for you. Thanks for watching. If you like that type of content, then please smash that like button and subscribe to the channel. Thanks for watching, and see you in the next one.